Okay, 12, 10, 14. This is the FIP quiz on angled launch projectiles. Okay, so for number 1, we have a delta x of 48.0 meters. We have our little football. I didn't draw it very well. And we have an angle of 27.5 meters. X, Y, blah, blah, blah. I'm trying to make this fast so we get it all in there. VIX, you know, we create all of our expressions for VI, etc. Well, what we know is that if time is our bridge, on the x-axis we can use delta t equals delta x over VI cosine theta. And on the y-axis, we know that overall, its y displacement is 0. So we can use delta y equals VIY delta t plus 1/2 a delta t squared and know that that's 0, which allows us to do our little magical bits here of -1 VIY delta t equals 1/2 a delta t squared, which allows us to get rid of a delta t, which now we have -1 VI sine theta, because that was VIY, equals 1/2 a, and we have a delta t, which is, of course, delta x over VI cosine theta. Okay, so at this point it's just algebra, which I know some of you think that's cruel when I say it like that, but it is, it's just algebra. This is the fun part, if you're a lunatic, I guess. So when we do all the algebra, we end up with VI squared equals square root of a delta x over -2 sine theta cosine theta. Plug in the whole, whoops, that's just VI equals that, sorry. Plug in the whole mess and you get 23.975, etc., or a VI of 24.0 meters per second. Okay. So, yeah, lots of you got that one right, and a few people, like I know I ran through one person's numbers and they had one, it looked like a calculator entry error here, and they got a wrong number there, and that made everything else wrong. So, calculator entry is a big deal. Okay, let's go to number 3 first, because that's going to be our fastest. So this is number 3. We have a ramp, much as young Mr. Dawson might build. I'm just guessing.
Many times.
15 degrees.
Mm-hmm.
And if you go 23 meters per second, you can get up.
Almost 2 meters in the air. Yeah. Now, we'll run the math if we have a few minutes to see how far up you can get in the air if you make it a 45-degree ramp. And remember, this is 1.8 above the end of your ramp. So if your ramp ends a meter off the ground, you're almost 3 meters in the air. Ugh. If at max height, at that point of maximum height, yes. Because that point of maximum height is where the velocity on the y-axis stops for a second. I know. That's okay. All right, and we have a VI here, which I realized later this was almost too easy. The tougher ones in your homework, you had this kind of problem, but you didn't have a VI, so you had to create an expression for VI. But that's okay. All right, so we actually don't even need anything on the x-axis here. We can treat the y-axis independently. So delta y max is what we're after. VIY is VI sine theta. Our old friend acceleration, -9.81 meters per second squared. And VF at max is 0. VFY at max. So we can use VFY squared equals VI y squared plus 2a delta y. Solving for that, VFY squared minus VIY squared over 2a equals delta y. That's 0. That's -1 times vi times squared times sine squared theta over 2a. That gets you your delta y. And when you plug it all in, you get 1.806130, etc. Or 1.8 meters off the ground is your maximum displacement. Now that's of course how far above your starting point you are. So yeah, if your ramp ends a meter off the ground, you're 2.8 meters up in the air. Okay, good with those? Let's look at number 2. This is really a lot like the monkey problem, and I have to go back and look at it. What we're interested in, so for every point on the x-axis, there is some corresponding point on the y-axis. We've gone through this before. What we want to know is at this particular point on the x-axis, when you are 50 meters out from the cannon, how high above the cannon's mouth are you going to be? Are you going to be below the level of the cannon's mouth? Are you going to be up above in the air of the cannon's mouth, up above in the air? That's what we want to know. So to do that, we have to create an expression that ties the two axes together. Of course, the natural point to do that is time. Now, in the monkey one, the book had you solve for time, the time at which you are 50 meters out. I prefer that you plug it back in. Of course, using this type of calculator, it's almost the same thing, because if you're doing those pieces of the equation separately, you're just pulling it down, so it doesn't much matter. Well, to create an expression for time at the 50-meter mark, we can do this. So we've got delta t equals delta x vix, and you're given vi, which makes this really pretty easy. To find where you're at on the y-axis at that moment in time, the easiest way to do that is delta y equals vi delta t plus 1/2 a delta t squared. And I'll move that up. Okay, well, and this is, of course, VIY. So now we're just going to plug this expression in here. What that gives us is delta y is equal to, so VIY is VI sine theta times delta x over VI cosine theta plus a, and I'm gonna skip a couple algebraic steps here, and if you object, just holler at me. Delta x squared over 2 vi squared cosine theta squared. Yes.
You know how we took one of the delta t's out at 2 during?
Well, you can only do that if delta y is 0. You can only factor out that delta t if delta y is 0. And you can't do it in this case. And this is the reason, and I had one especially obstinate young man last year in physics who insisted on writing every single derivation that we had ever gotten on his note card. I mean, this kid's note card was jam-packed. Yeah, every single derivation. So, VI equals square root of a delta x over -2 sine theta cosine theta. The problem you run into is things like this. Oh, well, that only works if delta y is 0. It's all conditional. And that's why I prefer, and I feel like you understand, I understand it better, and I think a lot of students do too, if you start from those 4 goldens, because then you're setting out the conditions in every case. You're setting out, oh, well, VI is 0, that goes away, then we can do this. Oh, well, delta y is 0, then we can do this. So that's why I prefer to just start from the 4 goldens, and it means you're doing more, in essence, what I'll call sort of, weight training with algebra. You're doing more algebraic training. You're practicing with those algebraic muscles more often. But what this kid did, who had every single derivation ever created on his note card, was he continually failed physics tests because he would plug in the wrong thing. Well, yeah, but VI is equal to this. Right, but only if delta y is 0. Well, but I have this derivation for delta t. Right, but that only works at this point, at top of flight. You know, that's my caution to you. So you can do it, but if you do, I would highly recommend that you have lots of conditions written down there, like this derivation works if delta y is 0. This condition works if delta y max, whatever. So anyway, we've got this. Now we can do some algebra. The VI's here cancel. Sine divided by cosine is tangent. So we have delta y equals tangent theta delta x plus a delta x squared over 2 VI squared cosine squared theta. Plug that all in, and what you get is a delta y of 22.25, etc. So what that's saying is that when you're 50 meters out from this cannon, you're going to be 22 meters in the air. Terribly written problem. I need to lower the angle on the cannon to make this at all reasonable. Or ask, here's the inverse way to ask this, and what would now I think be the better way to ask it. At what point will you be back at the level of the cannon's mouth? So at what point on the x-axis, whoops, do you end up here? And then you would solve for delta x, where delta y equals 0. And that's where they should put the net. You know, they're obviously not going to put the net 22 meters in the air. They need to move the net out further. So you're 45, they're shooting you way the heck up in the air. Okay? If you're apparently Jack or David, like I said, what you do on your own time is your own business. Yeah, 25 meters per second, 45 degrees gets you pretty darn high in the air. Now, think about that with regards to your bike pedaling. You don't want a 45-degree ramp. You don't want a 45-degree ramp. Okay, so nobody got 22.25. Nobody. I think there were lots of other approaches to this. Here's what I hate, and it's not as much of a problem for me as I mean, this is what, my fifth year teaching physics. I don't know how many times I've been down the physics road. I'll go ahead and stop this video for those of you who aren't here. These are the answers to the FIP. I'll have the key posted in the somewhere, maybe not the hall because it keeps getting stolen. Or you know, I'll take a picture of it and I'll put it on PBWorks. Yeah. Who wants a FIP quiz key? Seriously.
People really love physics.
Apparently, more so than I thought. Okay, so that's it.